Hello and welcome to the second video on calculus. In the previous video, we discussed the definition of sets. In this video, we are going to discuss operations with sets. So let's start. And let's start with two examples because the operations with sets are done on two sets or two or more sets. It cannot be done on one set. Okay, so let's take two sets. A is 1, 2, 4, 7, and let's take B as 3, 4, 5, 8. Okay, now let's define the first operation. The first operation is the intersection operation, which is A intersection B. This is denoted with this symbol, with this inverse U symbol, and this operation, what it does is it brings a new set which contains the elements which are common to both A and B. So the elements which are common to both A and B is the element 4, right? So which contains the element 4, right? So that is the first operation. This is the intersection operation. All it does is it creates a new set which has the elements which are common to A and B. Now let's move on to a second operation. Now let's define another operation which is called the union operation. It's denoted as A U B, A union B with this U symbol. What this operation does is it it also creates a set which contains all the elements which are in A or B. So we can choose from A and B. So we can choose all the elements from A and B, and because they have a common element which is 4, we avoid writing it twice. So it's the union operation is like writing 1, 2, 4, 7, which are the elements of A, and we get to choose from A or B, right? So we can choose both from A and B. So we also write the elements 3, 4, 5, 8, and since 4 is already in the first set, we avoid writing it twice. We don't include this element twice. So this set becomes 4. First we write the common element, and then we write the rest of the elements which are not common. 7, 3, 5, 8, right? So this is the union operation. All it does is it includes the elements which are either in A or B. So it's kind of like adding the sets together, but we don't add the common element too. Otherwise we would end up getting two elements in one set, two same elements in one set, right? Let's take another example. Let's take C to be 5, 8, 10, 12, and let's take D to be 6, 5, 12, 14. Okay, now let's define the operations on these sets. The first operation is the intersection operation, which is denoted with this inverse U symbol. This intersection operation creates a set which contains all the elements that are common to C and D, right? So what are the elements that are common to C and D? The elements that are common are 5 and 12, right? The rest of the elements, 8 is here but not in here, 10 is in C but not in D. So the only elements that are common are 5 and 12. So C intersection D contains the elements 5 and 12. That's it, right? Now let's define C union D. This set contains all the elements that are in A or B. So we kind of like add the sets C and D, right? So we add the elements from here and then from here. First, let's write the common elements from C and D, so we don't end up writing it twice, which are 5 and 12. And now let's write the other elements from C and D, which are 8, 10, 6, 14. And that's it. We are done with the first two operations, that is intersection and union. They are pretty simple operations. A nice way to visualize union and intersection of sets is Venn diagrams. And what we do in Venn diagrams is we represent a set with a circle, and because we define operations on two or more sets, we draw another circle with this overlap here, and this overlap is used for representing common elements, non-common elements, and everything else. So let's take the examples. Let's say A is 1, 2, 5, 6, and let's say B is 3, 4, 8, 10. Let's also include 5 here for obvious purposes. So how let's represent A with a circle, and let's represent B also with a circle, and we place a common element of A and B, which is 5, here, because then it will include in A as a part of this circle, and it will include in B. So it will show us that this 5 is a common element of A and B. And let's first denote this set is A and this set is B, right? Let's place the other elements of A and B. The other elements of A is 1, 2, 6, and these cannot be included here, right? Because these elements are only in A. Let's write the other elements of B, 3, 4, 8, and 10. So this is a Venn diagram representation of the sets A and B. So we can define operations with sets, the two main operations, union and intersection, directly with this Venn diagram. So the intersection operation, as you can see, is a common element of A and B, right? So what is the common element of A and B? It is 5. So it is shaded, and this part is intersection of A and B, A intersection B. And the operation, the union operation, how can we represent the union operation on Venn diagrams? The union operation is like adding the sets, right? So we include the elements which are only in A, and then we include the common elements, and we include the elements which are only in B. So we include this part, and we include this part, and we include this part too, right? If I draw the picture again, the union is only this part, because no, the intersection is this part, because it's the intersection includes only the common element of A and B, whereas the union includes all the elements from A and B. It's like the elements from A or B, so it includes the whole part, this whole part. Okay, now let's move on to another operation. This one is called the absolute complement. Okay, so now we are going to study absolute complement. Yeah, unlike other operations, this operation is defined only on one set. So if we have a set A, and the absolute complement is defined only on set A, and it is denoted as, so the absolute complement of the set A will be A raised to C. It's denoted like this. So this is the denotation, and now let's get into what absolute complement actually is. Let's do that by an example. So let's say that A is the set 2, 3, 4, 5, 6, and now we want to find the absolute complement of the set of this set A, and the absolute complement of the set A will be all other elements except the elements which are in the set A. So it will be everything other than the set A. Now where to choose the other elements which are not in the set A? For that we need to define a concept called as the universal set. So we are defining a concept called a universal set. This is denoted as U, and this universal set contains all the elements that are applicable for this particular problem. So this set will contain, for this example, uh, let's say it has 0, 1, 2, 3, 4, 5, 6, 7, and 8. So these are all the elements that are applicable for this particular problem, and the absolute complement of A, which says that we need to pick all other elements than those which are in the set A. Those other elements have to be picked from this universal set. So what we do is we just pick the elements in this universal set which are not in the set A. That's all. So we pick the elements 0 and 1 and 7 and 8. We pick these elements because they are in the universal set, but they are not in the set A. So these elements are the ones which we choose for the absolute complement of A. So this is just going to be 0, 1, 7, and 8. Now let's do another example. Let's say B is -1, 0, 2, 3, and 6. Okay, and we now know that in order to define the absolute complement of B, we need to first define the universal set, which contains all the elements. So let's say that the universal set for this problem is -3, -1, 0, 1, 2, 3, 6, and 7, 8. Let's just pick some random elements, and let's say that this is the universal set. Okay, and now we can define the absolute complement of B, because we now know where to choose the elements which are not in the set B. We should choose them from the universal set, right? So the absolute complement of B is the elements in here which are not in here. Let's pick those elements. We have -3, we have 1, we have 7, and we have 8. So these are the elements that we pick for the absolute complement of B: -3, 1, 7, and 8. Yes, that's all there is to absolute complement. Now let's move on to another operation. Okay, yeah, this new operation is called relative complement. Okay, this operation now is defined for two sets. Okay, so if you have the sets A and B, the relative complement is, let me just do it by example again. Let's say that A is 1, 2, 3, and 4, and let's say that B is 2, 3, 6, and 8. Okay, so the relative complement of the sets A and B is A minus B. A minus B, it is denoted as A minus B, and the elements in this set, the elements in the relative complement of A and B uh, will be all the elements that are in the set A but which are not also in the set B. So we choose the elements in here in the set A, excluding the common elements of A and B. Let's pick those elements. So we have 1, 2, 3, 4. Since we are doing A minus B, we choose the elements from A which are not also in B. If we do B minus A, we'll choose the elements in B which are not also in A. So that's one thing. And the elements in this set A minus B are 1 and 4, because 1 and 4 are the only elements in A which are not also in B. The rest of the elements 2, 3 are in B. So we pick these 1 and 4 for this set A minus B. So this set, the relative complement, contains elements 1 and 4. Yeah, now let's do another example. Now let's say C is a set 0, 2, 6, 9, and D is a set 6, 10, 11, 13. Now let's do D minus C now. D minus C is what? D minus C contains the elements that are there in D but which are not also common to C, right? Let's pick those elements. We can see that only 6 is the element which is common to both C and D. All of the elements that are there in D are not common to C. So we can pick those other elements which are 10, 11 and 13, and these 10, 11 and 13 will be the elements in D minus C, right? So this is just going to be 10, 11 and 13. Yeah, that's all there is to relative complement. Let's move on to another operation, and this is the last operation that we have on sets. This is called the symmetric difference. This is denoted by delta, and I will show this operation again with examples. So let's take, this is also defined on two sets, and let's take the first set A to be 1, 2, 3, 5, and let's take B to be 3, 1, 8, 4. Okay, so the symmetric difference A delta B, this set, the symmetric difference A delta B creates a set which includes all the elements that are in A and B but which are not common to A and B. So it includes the elements from A and B and it excludes the common elements from A and B. So all it does is it includes all the elements from A and B excluding the common elements, which is 1 and 3, right? So it includes the rest of the elements from A and B, that is 2, 5, 8, 4, and it excludes the other elements which are 1 and 3, right? Let's take another example. Let's name this x and y. Let's take x to be 1, 2 and 3, and let's take y to be 3, 4, 5. And now in the set x delta y, we should include all the elements which are in A or B but which are not common to A and B. So we should include the elements 1, 2, 4, 5, and we should exclude the elements 3, the element 3, because it is common to both sets. So in this set we have the elements 1, 2, 4 and 5. And by the way, if if we have if we have an example like this x, where x contains elements 1, 2 and y contains elements 3, 4, so there is nothing common to x and y. Then in the symmetric difference we include all the elements from x and y. It's like just like the union, right? And if the elements x and y are equal or equivalent sets, I will show an example. So if the x and y sets are like the following: if x is 1, 2 and y is also 1, 2, where there are no non-common elements of x and y, then the set x delta y will be an empty set, right? Why? Because there is nothing uncommon, or there is nothing different, there are no different elements from x and y. All the elements in x and y are common, right, to each other. So the set x delta y is a null set. So those are the operations of sets. The first is the union operation, the second is the intersection operation, the third is the absolute component, the fourth is the relative component, and the fifth is the symmetric difference. That's all there is to operations with sets. Thank you very much.